The fourth conference will be presented by Don José Tomás San José, is courtesy of Tecnalia Corporation Tecnológica.
Thank you, Mr. Chairman. Thank you to the organization of the committee. I would like to thank the kind invitation to Tecnalia Corporation. Just only a few words to talk about what is Tecnalia. Tecnalia is a private research company fully dedicated to innovation. That it means that we have merged from 8 different research centers in Spain, and we have different business. Only 2 figures to say that we are about 1,500 people, 12% we are doctorate, and we have about 120 million euros of income. In our business, one of the main business is the construction. In this line, we are working with different topics, and one of the main is the rehabilitation. In the rehabilitation sector, we have been working with Professor Thanasis Triantafillou and the Patras University from last 5 years ago. I would like to make a brief description of the curriculum of Professor Thanasis, in which we have shared different research projects, different PhD students, different topics. I would like to say, starting by the initiation of his career, he's a civil engineer. He developed his PhD in the MIT in USA. He has been a professor, actually is a professor in the civil department in Patras University in Greece, but he has been working such as assistant professor in the MIT and a visiting professor in the Swiss Federal Laboratories, CES like EMPA. In terms of more research curricula, I could say that he's author of 5 books, 15 book chapters, 50 international research papers in well-recognized journals. He has developed more than 100 papers in conference proceedings, 80 research projects. He has been involved in different private and public supported projects, and he has been received different awards. For example, I could say about the American Society of Civil Engineers, related with the Journal of Composite Construction Journal and Journal of Materials in Civil Engineering. I only would like to close, say these little words that he's really an expertise and a very well-recognized person in the topic of strengthening, for example, structures made of concrete and masonry. For example, I would like to say that his main research expertise is focused on advanced structural materials. I would like to say polymer composites, textile reinforced concrete. He's going to say something about this now in his presentation. And mainly focus his activity and his team activity in the Patras University related with repair and strengthening structures and seismic retrofitting. So this is the reason because I would like to present his presentation that is entitled Innovative Materials for the Rehabilitation of Buildings. Please, Professor.
Ladies and gentlemen, buenos dias. This is probably the only words I can pronounce in Spanish. Thank you very much, Mr. Chairman. Thomas, thank you very much for the kind words. I would like to thank the organizers for the very kind invitation to be here today, and Tecnalia in particular for giving me the opportunity to be here and present to you our latest research results in the area of advanced materials for the rehabilitation that includes strengthening as well as seismic retrofitting of buildings. Before starting, I would like to acknowledge the contribution of course, many of my students and my colleagues at the University of Patras, and also to mention that most of our research findings have been supported financially by the contribution of a couple of national projects, the main one being that one here, as well as by a European project, the project Opera, which was coordinated by Technalia and expired a couple of years ago. I'm afraid that my presentation will be a bit more technical. I promise not to show any questions, but you know, I am a materials guy, so I cannot avoid going into some details with regard to mechanical behavior of materials and structural elements. So after giving a brief introduction, I will talk about this new generation of materials, the so-called textile materials, textile-based composites. And we will talk about the application of those in concrete structures. We will specifically deal with confinement of concrete with shear strengthening and flexural strengthening. And then I will talk a little bit about masonry structures, how those masonry buildings can be retrofitted, can be strengthened with textiles when they are subjected to either in-plane or out-of-plane actions. Of course, my conclusions will come at the end. Of course, today there is a tremendous need for upgrading our houses, our structures, due to deterioration, environmental deterioration. That's one of the reasons. The change of use is another one. And seismic retrofitting is, of course, a very important reason, especially for countries in the south part of Europe, Greece, Italy, Portugal, Spain a little bit as well. So there is a demand for new materials and techniques. And as an answer to that demand, as a solution, I would say, engineers and researchers in the past 20 years or so have developed the so-called FRP, or Fiber-Reinforced Polymer method. They have worked with composite materials made of fibers, glass, carbon, or aramide, for example, basalt, fibers bonded together with epoxies, with epoxy resins to form the so-called composite materials. Those materials are not new. They have been applied in the aerospace industry, in the automotive, etc. But we, as civil, as structural engineers, have been using those materials in the form of strips, rebars, laminates, fabrics, etc., to strengthen our buildings and our bridges. This is a well-known method, one of the most innovative techniques today, which has applied with great success. You can see some examples here. Typical buildings strengthened in flexure with extremely lightweight strips. There is no need for scaffolding here. Those elements based on carbon fibers are bonded on slabs or beams. Similar products made of glass or carbon or aramide fibers are used to wrap columns or beams to strengthen them, to provide confinement or shear strengthening here in the case of beams. Those materials have also been applied and are being applied in historical structures, in monument-type structures like masonry structures, to strengthen them against earthquakes. For example, you can see a shear-type masonry wall strengthened here with CFRP laminates, masonry columns in churches confined with fiberglass. This is a photo before and after the intervention, and also arches consolidated with lightweight carbon-based strips. Those materials and the associated technique have many advantages, some of them being the very low weight, the extremely high strength in comparison with steel, the fact that we don't need to protect them They are quite durable. We can easily apply them in practice, etc., etc. However, we have a number of problems, a number of disadvantages. Namely, they are relatively poor behavior at high temperatures. Well, not so high, at temperatures which exceed the so-called glass transition temperature, which is about, say, 70, 80 degrees maybe. We cannot apply them on wet surfaces. They are not very permeable, which might be a problem when we deal with monuments, with historical buildings, and they are not compatible with substrates, such as those in monuments and historical masonry structures. Last but not least, we cannot perform assessment behind those materials in case of strong earthquakes. We don't really know what is happening behind those jackets, those FRP jackets, after a strong earthquake. So a few years back, we started working with a variation of that technique. We thought that it would be nice to replace epoxy resins with mortars, with cement-based mortars, for example, which are more user-friendly. Workers are very comfortable with those. They are much cheaper than epoxies. They have all the advantages of traditional construction materials. The only problem was that at that time we could not use those mortars to impregnate the fibers. We cannot impregnate fibers with those inorganic materials. To have a good, a meaningful composite, to fully utilize the composite action between the fibers and the matrix, that is the mortar, we need to use the fibers in the form of textiles. So we need an open architecture, a grid-like structure, which is penetrated by the mortar, by the cement or the hydraulic lime, for example, mortar. And hence we have the formation of a composite material with very high strength and stiffness that can be used exactly in the way that we use FRPs. The question is whether those systems are good enough. They can provide substantial strength, stiffness, ductility, etc. to our structure. So we started. I will go very briefly. We don't have much time to go into deep details, but I'll try to go very briefly to describe some typical testing cases which actually proved that those materials are nearly equivalent, if not better in some cases, with the classical FRPs, the polymer-based composites. So we started with, a few years back, about 10 years ago, we started with plain concrete cylinders confined with either FRPs or those, I should go back to my previous slide to give a definition, to give a name for those materials. We use the term TRM, textile reinforced mortars, for those materials. So we wrapped concrete cylinders with FRP and then with TRM, and we looked at typical stress-strain plots. Red curves here show the response of unconfined concrete, and then blue shows the response of concrete confined with FRP here and with TRM there. We see that TRM is not as good as the FRP in this particular case in terms of strength and deformation capacity. But if we compare it with the control specimen, that is the one without confinement, it is quite good actually. We have an increase in the strength, and we have a dramatic increase in the deformation capacity. Then, I'll skip that, of course. Then we moved to larger structural members. We looked at columns. We looked at what is happening at reinforced concrete columns when subjected to earthquakes, to seismic action. A typical failure scenario is buckling of the longitudinal reinforcement at the ends due to heavy compression stresses in those compression zones. And an easy way to prevent that or to delay that is the so-called local jacketing, that is wrapping of the ends with fibers in the circumferential direction. Of course, this is done today with FRPs, and we try to do something similar with the TRMs. And to have a good understanding of that, we started with small prisms, with small cross-sections 20 by 20 centimeters, confined with FRPs and TRMs. I'll show you some photographs. You see one of those confined with the TRM system, an identical specimen wrapped, confined with the FRP system. Those systems are equivalent. That is, we have exactly the same amount of fibers in the circumferential direction. The only difference is in the matrix. Here we have epoxy. In that case, we use a cement-based matrix to bond the fibers. And we started with uniaxial compression testing of those members. You see buckling of the internal reinforcement in the case of the unconfined members, and fracture of the FRP, but also of the TRM jackets in the case of confined specimens. The fact that we have this fracture indicates is the best proof, actually, that the fibers, that the materials are fully utilized, that we can utilize the full strength of the fibers. We don't have to look at all those curves. Just remember that in each family of those curves, green is the response of the concrete prism without any jacketing. Blue lines, blue curves correspond to the response of the specimen with TRM jacketing, and red curves correspond to the response of the specimen with the FRP. So if you compare blue and red, you see that they are not that far apart. The effectiveness of those systems is similar to that of the FRP system. The next step was to verify exactly the same failure mechanism in larger scale members. We tested columns, full scale columns, cantilever type specimens subjected to horizontal displacements to simulate the effect of earthquakes. You can take a look at some photographs here. So those specimens were confined only at the bottom with FRP or TRM jackets. I have some results which illustrate how the control specimen, the control column, that is the one without jacketing, behaved. We have a relatively sudden fall in the strength, reduction in the strength due to buckling of the longitudinal reinforcement at the base of the member of the column, in the unjacketed member, in the one without the jackets, whereas in the case of the FRP or the TRM jacketed columns, we have a much better, much more ductile response with stable hysteresis loops and the dissipation of a substantial amount of energy. So we could conclude here that the two systems are practically equivalent and much better in terms of deformation capacity in comparison with the control specimen. The same concept was tested in a nearly full-scale building in our laboratory. We made a two-story reinforced concrete frame. We tested this frame before strengthening, but also after strengthening with those TRM jackets, which were applied locally only at the ends of columns to provide ductility. The building was tested up to 0.45 G. After retrofitting, after strengthening with those jackets, that's a substantial acceleration. That's a relatively strong earthquake. The conclusion was that the jackets behave extremely well. I think I have a video, a very short video, that illustrates how the building was tested. If I manage to play that, okay. Yeah. You see loading of the building and without any failure at all in the jacketing system. I will skip that. We did similar tests to prove that those materials can also provide very good confinement at the base of columns when we have lap splices, which is quite typical when we have short lap splices, which is quite typical in old reinforced concrete frames. Our conclusions in that case are exactly the same, that both TRM systems and FRP systems are practically equivalent. They provide the same level of confinement at those lab-spliced areas. And then our next step was to combine those confining systems with longitudinal reinforcement applied on columns to provide flexural strengthening. So we confine columns strengthened in flexure. We confine them with TRM at the base. And again, it was interesting to observe that if we compare with the control column, there was substantial increase in the confinement, in the flexural capacity due to this external confinement. The next step was to work on shear strengthening. I have been talking on about confinement so far. Shear strengthening is quite frequently critical in beams and columns, so we designed members that would fail in shear intentionally. The failure mode should be shear, a brittle one, and those members were tested before strengthening and after strengthening with FRPs or TRMs. You see a typical brittle diagonal shear failure of a beam without any strengthening in the shear span. That's the response in terms of force versus mid-span displacement. This is the response of the member, and how those load versus displacement curves change, and how the failure mechanism changes from brittle shear to ductile flexural when strengthening of those members in the shear spans is done with either FRPs or TRMs. So again, our conclusion here is that the system is equivalent to the well-known FRP system. The next set of experiments dealt with flexural strengthening of beams. In that case, the reinforcement was bonded externally on the tension zone just below those beams to increase the flexural capacity. A typical response of a member without flexural strengthening is the one shown by the black curve. We see at force versus mid-span displacement curves here. So this is the beam before strengthening. Blue illustrates how that identical beam would behave after flexural strengthening with FRP, and red is the corresponding curve for the case of strengthening with the TRM system. So we have an increasing capacity, but not as high perhaps as in the case of FRPs, but we also have an increase in deformation in ductility if we compare the system with the FRP system. Flexural strengthening of beams with those textiles is probably not a very good idea because we don't utilize the fibers in the transverse direction, so we have to use a hybrid system here. But it is certainly a very good idea when we deal with two-way slabs, with slabs in buildings. Given the fact that we have fibers in two directions in those textiles, we can use those fibers to carry tension forces, tension stresses in two-way slabs. We tested a number of those in our laboratory. You see, for example, the load versus deflection curve of a slab without any strengthening. It is this curve here at the bottom. And then how that can increase, how the capacity, how the flexure resistance of the slab can increase depending on what type of textile, how many layers we use, etc. So again, our conclusion here is that the system is quite promising also for this case of two-way slabs. In our last series of experiments, we were interested in looking at the response of masonry, unreinforced masonry structures, especially subjected to earthquakes. But not only. Wind could also be a possible case, but also other types of loads. If we look at how masonry fails subjected to seismic actions, we can identify several different failure modes and the corresponding elements. For example, we have shear walls, masonry shear walls, which fail due to diagonal tension. We have masonry walls which behave very much like slabs, unreinforced slabs, and they fail in flexure. We have column-type elements subjected to in-plane flexure in combination with axial loading, or beam-type, deep beam-type elements subjected to shear, flexure without axial loading. So in an attempt to get a better understanding of all those different failure mechanisms, and also with regard to the use of TRMs, we designed several wall edges, relatively small wall-type specimens which we tested in the lab before strengthening and also after strengthening with FRPs or TRMs. I will just give some indicative results to see the comparison between the two systems. A shear wall, for example, subjected to in-plane shear in combination with axial loading. In-plane shear is provided by an actuator in a dynamic way, so we have cycling of the loading. We always look at load versus midspan displacement curves, just to have a way of comparing the results. Red, in all cases, is the response of the wall of the masonry before any retrofitting, before strengthening. So there is a relatively low capacity. And then you see how the strength, but also the ductility increases. We have a number of cycles of loading if we use the FRP system. And then you see exactly the same, well, I would say a similar response, similar results for the case of the TRM systems. When we look at different types of structural elements, that is column-type structural elements with an axial load and cyclic bending and shear, again, red is the rather poor response of the control, that is the unstrengthened wall, and then you see how the strength increases if we use the FRP, and what happens for the case of the TRM. Here we have a dramatic increase in the ductility also. Masonry subjected to out of plane, again, our strength is practically zero here in the absence of axial force, but we have a very high capacity if we strengthen the system with the FRP or the TRM. There are a number of practical applications of the technique already, some on concrete, reinforced concrete buildings, others on masonry. You see some photos here. We can see those textiles in the form of diagonal strips to strengthen masonry, masonry walls, or to consolidate domes in historical buildings. This last application is from Greece. The designer here specified a lightweight jacket to consolidate the dome from above. There was no way to have access from below. That could not be done. It was forbidden to be done with polymers due to the lack of compatibility. It was done with the TRM system, which was anchored on the wall, also using those special types of spike anchors. I think that was my last slide. Well, that's probably the last one. Another application from a historical church in Cyprus, in the city of Paphos in Cyprus, where this bell tower had to be rebuilt, to be reconstructed. It was done with bricks strengthened at the interface with a mortar, with basalt-based textiles bonded with compatible to the bricks inorganic mortar. My conclusions are that we have at our disposal a new technique for strengthening and seismic retrofitting in general for the rehabilitation of buildings using those textile-based products. If we compare them with FRPs, which are well known to the research, to the engineering community today, those materials behave in a similar way. They are at least as effective in most cases. In some cases, they are even better, in the case of masonry, for example. And we feel that this is at least an interesting alternative which should be used more and more in the future. With that, I would like to thank you very much for your kind attention. Thank you.
Thank you, Professor Triantafillou. Your interesting was very interesting. And now, before some advices for the next things in the Congress, I would like to thank again to the Colegio of Oficial of Ingenieros de Telecomunications, to Tecnalia, to the Colegio of Civil Engineering, Colegio de Ingenieros de Caminos, Canales y Puertos, and to the Colegio of Ingenieros Técnicos de Obras Públicas for your sponsor of the sessions. And now, two things. We would like to do a family picture in the staircase of the entrance. Just 2 or 3 minutes, please be with us to the picture. Later on, we will have a coffee break of around 20 minutes. We are a little late, but I think still, I think we can manage the session, next sections, to be more or less on time to the lunch time. Thank you. Now is the break time.